Welcome to this lecture, which is about the mathematics needed for understanding uh, algorithms, especially RSA algorithm. We'll start with very basic concepts. Some of you may definitely be knowing those concepts, but it will be very good to revise. Let us start with greatest common divisor, which we usually study in primary classes. Now, what is GCD? Or it is any positive integer, suppose C, which is common divisor of A and B, provided it satisfies two conditions. Condition number one, that this positive integer C is said to be greatest common divisor. The two conditions are: one, that this C is a divisor of both A and B, okay, and any divisor of A and B is the divisor of C. Let's do one example. Very simple example. Let's find GCD of 4 and 6. So let's see which number is getting divided by both. Okay, so 1 is obviously a number which gets divided by any number. So let's start with 2. Of course, we can divide 4 by 2 is 2 and 6 by 2 is 3. But now we want to find greatest common divisor. Let's move to 3. Although 3 gets divided by 6, but it does not get divided by 4. And let's move to 4. Of course, 4 is divisible by 4, but it is not divisible by 6. So it means we cannot move beyond 2. So hence GCD of 4 and 6 is 2. A very interesting case is to find GCD between two numbers which are co-primes of each other. Let's take an example of suppose 7 and 11. What do you mean by co-prime? So 7 and 11 have no common factor. Okay, so they have no common factor other than other than 1. Now what is the GCD of both of them? Of course, the only common factor between them is 1. So it is 1. This is very important result. So if P and Q are co-prime to each other, then GCD. Now it is quite clear that for large numbers, finding GCD can be tricky. It can take time. Let's devise some algorithm. Suppose let's take this case of GCD between 4 and 6. Okay, let's denote the numbers A by 4 and B by 6, and let's put a norm that this B should be less than A, or A should be greater than B. So in that case we will swap. We'll swap like this. We'll store say A as 6 and B as 4, and so GCD is here in that sense commutative, the same as GCD between 6 and 4. Now what we will do to find GCD, the first step, let's divide 4 by 6. So we have a remainder 2. Okay, and now let's save this 2 as B. Okay, so this was actually remainder R, and we now replace this B is equal to 4 with B is equal to 2, and again divide. So this A is equal to 6, we divide by B is equal to 2. So we got the remainder 0. So once we get the remainder 0, this number 2 we know that is GCD. Okay, so this trend is true for all sort of numbers when we want to find GCD, and it was first, you can say, discovered by great mathematician Euclid, and it's called Euclidean algorithm. Here is the general form of Euclidean algorithm. Whenever you want to find GCD between any two numbers, suppose A and B, first check if A is greater than B. If it is greater than B, then nothing to do. If A is not greater than B, just swap as we did in previous case. So A was A was 4 and B was 6. So since A is not greater than B, we swap it. If it is, fine, divide A by B. So you can think of dividing 6 by 4, and the remainder R was 2. Then here, okay, check, is R greater than 0? Yes, 2 is greater than 0, r is not 0. So we will basically go to this part. So yes is here. Yes, r is greater than 0. So replace a with b. Okay, so you have to replace a with b and b with r. That is, you have in previous case a is now 4, fine, and replace b with r, so b is now 2. Now we divide them again. 4 divided by 2 is 2 and the remainder is 0, fine. So remainder is 0. R is greater than 0? No, it is 0. So GCD is the final value of b, which is 2. So this is how this algorithm works. We don't need to go, it's in its implementation. You can do it as a dummy exercise, but we just need to understand how GCD is being found, because this will be a very crucial step in RSA, as you might have already seen that in the previous class also. Let's recall the modular arithmetic. Any number a can be written as qn plus r. Basically, if you divide this a by number n, so what remains at the end remainder is r and the quotient is q. Okay, so this is a very simple relation. Of course, the remainder can never be greater than n. For example, 13 modulo 5. So what you do is, so you divide this 5 by 13. So the remainder is 3. So this 13 modulo 5 is 3. There are some properties of this modulo operation. The first more important thing is, suppose if we have a modulo n and also b modulo n, if these two are equal, then we say that a and b are congruent. 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 Okay. In some sense, they are actually equal under modulo n. So we write a like this, and in the bracket we write here modulo n. Okay, so it is not a normal equality. It's not like a equal to b. Rather, the modulo operation of a with n and b with n result the same number. A very simple exercise to do. Divide 73 with 4 and 23 with 4. The remainder will be same. So 73 is congruent with 23, but under modulo 4. Also, we have done this in the class also. I will recap it. So if you have two numbers, so a and b, and you do this a modulo n and b modulo n, whether you add them, whether you subtract them, or whether you multiply them. So this is same as before that we will take one more modulo n of this whole. So this will be equal to a. If you are adding, it will be a plus b. If you are subtracting, a minus b. If you are multiplying, a times b, but again modulo n. This is very important property, especially the multiplication property, that is a modulo n times b modulo n whole modulo n is equal to a times b modulo n. Now let's illustrate its application in finding the exponential modulo of exponential. Let's see. Let's say you are supposed to find 11 to the power 7 modulo 13. So doing it conventional way is not convenient. So let's see how we can use the property. Okay, let me make it simple. So we'll do it step by step. So first of all, let's see 11 mod 13. So we know that it is 11 because this we have done once for all. Whenever this number which we from which we are dividing 13, with which we are dividing 13 is smaller than this dividend, then the result is number 11 itself, because the quotient here is actually 0. Okay. Now what about 11 square mod 13? So we'll use this result. You see here a is 11 and b is 11, fine. So then if we write like this, so it is equal to 11 into 11 mod 13. Okay, uh, which is equal to 121 mod 13. By simple division we will observe that 4. Okay, you can basically do like this: 121, you see it's 9, 117 is 4. Fine. Now let's do next 11 to the power 4. Okay, so yeah, yeah, 11 to the 4 mod 13. So now how will we proceed? We can write this as 11 square times 11 square mod 13. Now using this result, so take 11 square as b, this a, and this 11 square as b, this as n. So we'll use this result. This is equal to a mod n times b mod n, this with mod n. So it becomes 11 square mod 13 times 11 square mod 13, whatever we get, mod 13 again. So 11 square mod 13 is 4 into 4 mod 13, which is 16 mod 13. You can quickly do it. So 13, so 3. So this answer is here 3. Now how can we write 11 to the power 7 mod 13? We can write like this. So 11 into 11 square into 11 to the power 4 mod 13. Fine. So this is same as 11 to the power 7. So now we'll use the result again. So this is equal to 11 mod 13. It is the product like this times mod 13. So we know 11 mod 13 is 11. 11 square mod 13 is 4. 11 to the power 4 mod 13, we just now got 3 modulo 13. Fine. So this is, I think, 132 modulo 13. When you divide it with 13, so it is like this. So basically 132, and 13 times 10 is 130, remainder is 2, so this is 2. Now you see 11 to the power 7 modulo 13, we got 2. By using the modulo arithmetic properties, if you do it directly, it is very lengthy and cumbersome, just writing here 11 to the power 7, then dividing it with 13, it will be very lengthy. So exponentiation in modulo operation can be simplified by using this operation. It will be used in RSA algorithm, as you will see. Next we state Fermat's theorem, which we see that like this: if p is a prime, if p is prime number and a is any positive integer not divisible by 2, that is not by p, that is p is not a factor of a, p is not a factor of a. Okay, then Fermat's theorem can be stated in this way: if you take a to the power p minus 1 and do it modulo p, then it is equal to 1. Okay, and since 1 can be also written as 1 modulo p because p is greater than 1, so hence we can write that a to the power p minus 1 is congruent to 1 under modulo p. Okay, so if this becomes difficult for you, we can simply look at like this. So let's do an example. Suppose a is 7 and p is 19. Then it means we have to basically compute 7 to the power 18 modulo 19. Of course, this is a very complicated operation, but we'll again use the arithmetic properties of modulo arithmetic. So let's start with 7 square. 7 square modulo 19 can easily find. It will be 11. Then you can take another power of 7 as, suppose, 7 to the power 4. modulo 19. You know what we actually are doing. Let me elaborate the second one. You are basically breaking this into 7 square into 7 square modulo 19. Then you are applying the multiplication property of modulo. So you take 7 square as a and another 7 square as b and 19 as n. Then this becomes 7 square modulo 19 multiplied by 7 square modulo 19, then whole modulo 19. Then after simplifying this, you will get 7. You can check it. Okay. Similarly, you can take another power of 7 as 7 to the power 8 and 7 to the power 16. So 7 to the power 8 modulo 19 and 7 to the power 16 modulo 19. And you can verify it. This will be 11 and this will be, I think, 7. Now 7 to the power 18, how to compute it? You can write it as 7 square into 7 to the power 16. Now you want to do modulo 19. Again, use the property, simplify it, you will get the answer equal to be 1. So this is the verification. We will not do the proof right now. So remember that you have any integer, positive integer a, you have a prime number p minus 1. P should not be factor of a. You take modulo p, this will be equal to 1. Okay, so this is the main result. You will see it will be used in RSA algorithm somewhere. There is another way to state the same result. It says that if you write it like this, a to the power p modulo p, then this will be equal to a. Okay, so basically how do you say this? So a to the power p minus 1 you can write as a to the power p divided by a. Okay, so this a you can multiply here. This is more popular form of this. And when you write it in this way, then you don't need that p should not be the factor of a. Anyway, this is another way of stating the Fermat's theorem. And at times, whenever we have any such, suppose you have 5 to the power 17, you see, and someone tells you that find its modulo with 17, it is needed at times, and you don't need to anything. So this a is equal to here 5, p is equal to 17. Using this result, this is simply a, which is 5. Without any second thought, you can use Fermat's result. Okay, so this simplifies exponentiation whenever we have the exponent is prime number. Next, we define Euler's totient function, which we have defined in the class also. So it is denoted by phi of n and is defined as number of positive integers less than n and relatively prime to n. Okay, so it's very simple thing. Suppose we have phi of 6, fine. So let's write positive integers. 1 is there, 2 is there, 3, 4, 5. Okay, less than 6 we have tried. So now is 1 and 6 relatively prime? No. 2 and 6 relatively prime? No. 2 and 6 have a common factor, 2. 3 and 6 have a common factor. 4 and 6 have a common factor. 5 and 6 doesn't have a common factor. So phi of 6 will be equal to 1. Let's do one more example. Suppose if you take now a prime number, let's say phi of 11. So all the integers less than 1, 2, 3, 4, 5. So 1 is actually here, it's not needed. 5, 6, 7, 8, 9, 10. So is 11 having any common factor with any of them? No, 11 does not have any common factor with any of them. So how many numbers are there which are relatively prime with 11? All numbers less than 10 are relatively prime, so phi of 11 will be 10. Okay, in fact, if you have any prime number, you will see this, that if you have any prime number p, then phi of p will always be p minus 1, because it's a prime number. It does not have any common factor with any of the previous numbers. Let's suppose if someone asks you phi of 37, the only thing is you must be doing that 37 is a prime number, so this will be definitely 36. Okay, so if a number is not prime, then you really need to count. You really need to find that how many numbers are there which are co-prime to each other. Suppose if someone asks you phi of 10, let's say, so you see 1 2 3 4 5 6 7 8 9. Okay, so 9 is relatively prime with 10, 7 is relatively prime with 10, 3 is relatively prime with 10. Okay, and 1 is taken by convention, so 1 2 and 3, so 1 2 3 4, so phi of 10 is equal to 4. Okay, so this is the totient function, and there is very important result. Suppose you have p and q are prime numbers, and let's say n is equal to p times q. Okay, then the totient function of phi of n will be equal to the totient function of each prime number in their product. Okay, but we know that if p is a prime number, then its totient function is simply p minus 1, and sorry, it's q is a prime number, so it is q minus 1. This will be used in RSA algorithm, this result. Okay, so if a number n is product of two prime numbers, then the totient function of n is very easy to compute. Now we have very important extension of Fermat's theorem in terms of totient function. It's called Euler's theorem. It says that if you have any number n, right, and you can then find its totient function, suppose phi of n, then take any positive integer a, so a to the power phi of n modulo n will be equal to 1. So we do not again prove it. We can write it in another way. So a to the power phi of n is, since it is modulo n is equal to 1, which we can also write as 1 modulo n, because n is greater than 1. So we can write then a to the power phi of n is congruent to 1 in modulo n. Okay, so this property is also used in RSA algorithm. But there is very important condition that a and n must be relatively prime to each other. Well, these were some important mathematical concepts. You will see that they have been used while describing the RSA algorithm very repeatedly. If we may need some more concepts that I will introduce on the go, but I think in this lecture I have tried to combine all the basic concepts, of course without proof, right? That needs a lot of time, which will be used in our subsequent lectures. Okay, I hope it is useful, and do some practice. Take some prime numbers and take some number a, and you can do some practice to get hold on these results. Thank you.